Okay, if so what I want to show is I want to show the converse for when you have a parabola, yeah? So we kind of talked about that a little bit. So we have E equals 1, yeah? And you're given a directrix, yeah? Any line and another origin that's a point that's different to the directrix. And you want to show that the locus of all the parabola, basically the equidistant points, right, is gotten by reciprocating a circle, okay? And so what we did was, so for simplicity, the book says to set the center, obviously we have to set the center at O, and we set the radius to be OA, yeah? Um, so not OA, but the radius to pass the circle to touch at A, yeah? The circle A might not go through O, yeah? But for the parabola it does, yeah? Okay. And we basically want to show that every point on the parabola, or every point that's equidistant from those two things, is gotten from the reciprocation of this circle, right? Um, yeah. So the radius will be OA, yeah? Define the radius to be, you know, OA on epsilon. Yeah. Okay, so for the parabola, you can kind of see, so basically, for example, you take the midpoint here, right? Yeah, the midpoint. Then the point that's here, the midpoint is half OA, right? And then this point here, the end point there is OA to OA, yeah? Okay? So then you can see that this point inverts to that point, yeah? Because they times together to be OA squared. Okay? Now, okay, so we know there's one point that's equidistant from O and the line here. That's it. Okay, for every other point, it's symmetric about this x-axis. Okay? So we only have to show that sort of for every distance here, okay, so for every distance here, so everything that lies along this vertical line, right? Well, there's only one point on this side of this line that has the right distance from O, right? So for the parabola, we're going to show PO equals PK, yeah? And so there's only one point on this side of this symmetry line that is equidistant to PK and PO, yeah? Okay, so we find that point, yeah? Okay, we find that point, and then we join it to O, yeah? Okay, now we join, and we want that point ultimately to be the pole of some tangent line of the original, on the circle we're trying to reciprocate, right? So we want it to be like a T, yeah? Okay, so how do we find T? Well, we can just take a line parallel to OP to A, right? So that's going to make this perpendicular, and it's going to make this perpendicular, right? Because they're parallel. So you know which point on the circle has to be, right? So you draw the tangent, it has to be perpendicular. So basically what you want to do is you're hoping that this intersection here inverts to there, right? They need to invert to each other, okay? And so basically, you know what happens? Like you know wherever this point inverts to, right? It satisfies PK equals OP, yeah? It's equidistant from directrix and focus because that was the converse of what we were trying to prove, right? So no matter where this goes to, it will be equidistant, okay? So I mean, imagine if it goes somewhere past this point, right? You have like, so this length here, they're equal, right? So this is K, this is O, and this is P, yeah? And then if your inverted point isn't P and it goes further, right? It goes to like here. It goes to Q, right? Then what do you have? Well, you have this weird situation where basically you're saying that these two parallel lines, right? So this is like this is the directrix, yeah? So this is the directrix. They're basically saying like this is equal, and then when you extend it further, this whole thing is equal to this whole thing here, right? But that's impossible because yeah, for example, if you join this line, if you join O to K, right, and kept going, yeah, that would be this whole distance would be the thing that's equal to x, because this angle is equal to this angle because they're isosceles, right? And then it's equal to this one because they're parallel. So then you're missing that margin there, okay? So so you have that. So if you move past P, right, and it can't be isosceles anymore, yeah? And actually that same argument shows if you didn't go far enough and it's isosceles, or you just switch the roles of P and Q, and then you have the, it can't be isosceles again, right? So basically, if this is the point that's isosceles, yeah, there can't be another point on that line that's also making this PK equal to OP, okay? So, and we can fix this line, yeah, so we fix this distance first, find that line, and then we can't find another point there, right? But we do find that it can be the inverse of some point on that line, right? So basically what we're saying is for any distance from the directrix, we have a point on the conic, yeah, that satisfies PO equals that distance, okay? So basically showing that the conic doesn't have any gaps inside the parabola, it's the whole set, okay? So another way of seeing this particular little lemma, I mean, it's kind of obvious if you think about it. You have a parabola, right? Yeah. You're basically saying any point here, you draw in the focus line, yeah? It doesn't meet the parabola again, okay? Because if it meets it again, that's when it's equidistant again, right? Yeah. Okay, but then see, this can generalize for the other curves too, right? Because if you know what the ellipse kind of looks like, yeah? If you know that you have a focus and it looks like that, right? Then you have a point, you just need to know that it doesn't touch it again, right? So there's no 2 points that make the right ratio, okay? Yeah, but the details of which you'll have to fill in, but we did it pretty specifically for this parabola, okay? And we didn't have to know too much, we just had to get something on that line, yeah? Once we got something on that line, then it would have to be that point. Okay. So that's the rest of 6.3, 6.4. 6.4.